This is just with, a handful of particles running on a single ship. This is not accounting for if you've got, 10, 20, 100 ships, you might then want to look at this as more multiplicative. Hey, you guys, Space Marine 658 here. Welcome back to episode 2 of our Converting Blueprints to C++. This is the intermediate episode. So on this, we're going to touch on a little bit more advanced topics. We're going to touch on things not quite as simple as the last one. We're going to touch on, Niagara particle systems. We're going to touch on things like for each loops, just some extra little bits here and there. So let's go ahead and dive right into it. Starting off in our blueprints, we're going to basically convert this massive mess that I've reconstructed based on older code of mine to kind of show off what it looked like before. And it's going to convert down to this very simple 3-node structure. Now, even this itself, I could convert even smaller, but I like this because it's a little bit more flexible and it kind of can allow me to kind of show off what I'm working with. With this, let's go ahead and first take a look at what we were doing before. So to kind of give you an idea of how this actually worked, basically I had a check here where I would say, do these tags exist? If they exist, then we're going to go check our particle setter. The reason for this is mostly for some flexibility. So if I have ships that don't have one of these tags, I'm not setting particles when I shouldn't be. And it probably could be broken down even further into just checking on each one. And then only firing particles for that one. But I kind of grouped them together in a way that I think makes sense for now. And then the C++ code will be much easier to make that a little bit more broken down later. From there, I would then go, if we have that, then we're going to take the thrust input and we pass it in, and we pass in these as well into a particle setter function. And for some of the different ways, into a counter particle. So let's kind of show off what that looks like, right? So if we go ahead and load up the game here, as you can see, we're going to have a couple of different engines on the ship. So for example, we have our thrust forward, thrust backward, yaw right, yaw left, pitch up and pitch down, and then of course our roll right and roll left. Now with that, some of these engines, as you may have not noticed, do something called a counterbalance. So for the players, I wanted to simplify things a little bit. They're still going to have a lot of control over the ship and how it flies, but I don't want them to have to start yawing and then counter yaw and things like that, at least not in the current iteration. I wanted to simplify the 6 degree of freedom a little bit. So there's 6 degrees of freedom. You can move in any of the 6 directions. But for example, right, if I yaw to the right and then let go and not touch any keys, you can see it kind of slows down and we have those particles firing in the opposite direction. And that's so that the player can start spooling up, start spinning, and then it'll slowly come to a rest without the player having to actually sit there and counterbalance it. Now, something like the thrust does not have a counter particle. Instead, you just got to slow it down yourself, or you can hit the brakes in the game, which will basically align you with your velocity vector and slow it down for you. That one's still being tweaked a little bit, but it works pretty well. And so with that, I've got a lot of different particle systems on these engines, but I want to have it in a unified control system so that for the most part, it works how I would expect, and I can reuse it for the AI. I can reuse it for allied ships. I can reuse it for anything I want within the game. So let's go ahead and take a look at how that was done before. Now that we've got a better idea of what these two functions are supposed to do. So what would happen is I'd pass in my input for the particle setter. It would come in here and say, is it nearly equal 0? If yes, then it would go and set the parameter to 0. Basically, if you were almost to 0, it would basically start hiding the particles. But if you were not, if you were actually putting in some input, then it would go and it would just set whatever for example, here I'm just using a tag. And this is just linked to a value inside of my player that is then, or I guess technically not even the player, this is also on the AI. But any system, any component that has this attribute, and then it's returning a 2000 here for the parameter, or times 2000 that value, because basically that's just a way to ensure I'm getting the proper amount of particles there. But even within this, as you can see, there's a lot of for each loops. And there's even this where I'm checking, is the input less than or greater than 0, basically a way to tell if I'm going forward or backward. And then I'm also getting the particle system from that tag. I'm just doing a whole lot of stuff here inside of blueprints, and these can get quite expensive. And that's just for the first function. Then we also have a counter function on some of these, a counter particle. This basically does a check, and it goes, is the current speed greater than or equal to 0.01 absoluted, so no negative or positive. And then it goes, is the input also equal to 0? If both of these are true, then we're going to trigger off the counter particle. Now, the counter particle is just another particle setter. So again, going in and possibly going through multiple for each loop. So at the very least, it's going through one for each loop, but it could go up into at least 2 if our input is nearly equal to 0, which for a counter particle, it would be. And so what this would do is it would go in, it would go, okay, our input's nearly equal to 0, therefore, we're going to fire off both of these, setting it to 0. But then this part over here is actually overriding that a bit by having the current speed be passed in. So it would then go, okay, here's the current speed. Then it's going to go in here, and instead it's going to actually, depending on what the current speed is, if I'm going negative or positive, it's then going to override the particles based on that. Now, once my counter particle gets 0, or gets near 0, then it'll trigger off up here and hit both of these, setting it equal to 0. So this is a lot of code that's being reused. So one of the most useful things then is, turning that into C++ instead of leaving this all in blueprints, right? But we don't want to have all of this stuff as input parameters. So instead, what we're going to do, and what I did, is create a struct. So this is a use struct, a blueprint type with a meta of a short tooltip. And in here, I just created an fparticles struct to just pass that information to the front end. So basically, pass it from the front end to the back end. So what I'm doing here is I'm taking and combining all of these, what would normally be input parameters as I was using them in the blueprint, and just basically making them as inputs into the struct. So I have a T array of F names, so that's just my tags for the forward engines. And then I have some for the rear, pitch down, pitch up, so on and so forth. And then down below, I've got floats for all my different inputs and pitch speeds and yaw speeds, and for my translate X and Y. And then I've just set it to a default here for some of those. You don't strictly need this, but I like to at least set some of that stuff to defaults. From there, I went ahead and created my actual 2 hidden functions. So these are member functions that I'm not exposing to the blueprint. The benefit of doing this is that by not exposing these, I can, 1, pass in a little bit more information. 2, they don't clog up my UI because I don't need to see them. I'm never going to access these directly, or I shouldn't be accessing these directly. And it allows me to do a little bit more with these that I probably couldn't do inside of blueprints directly, because something a lot of people don't know is that in blueprints, the reflection system doesn't reflect every single possible input type. So for example, any parameters, right? You have your float. If I wanted to have this be a blueprintable function, I couldn't include certain things. Like I want to say it's int 8. I believe int 8 and other kind of off angle, data types cannot be passed in the reflection system. I don't know all of them off the top of my head. Of course, there's so many different data types, but you can find out pretty obviously when you try to add them to a blueprint callable function, and it just won't work. It won't let you do that because they're not in the reflection system. So I've got these 2 member variables right here, member functions. And these I call within my actual U function up here. So this U function is that check particle states. So if I go back to my blueprint here, right? What I'm doing is I'm making that struct. So that struct that I talked about earlier, I've created a reference to particles, that struct. And I passed in all of this information, and then I just returned it here at the return node. From there, it's gone ahead and passed into a set particle structure by ref, and I'm setting that reference variable to that value. From there, I'm then passing that reference struct into that function, that check particle states. And of course, I'm also passing the get owner. So if we go ahead and look at the function, what it's actually doing is it's taking a const to the f particles address, a particle collection, and then it's taking a pointer to the actor, which is the owner. From here, if we go ahead and hit control and click on this function, will take us into our function library here. And what we're doing is basically very similar to what we're doing in the blueprints, but we're doing it inside of C++. We're basically going if this is not empty. So if we've got some kind of tag in here, and we got some kind of tag in here, and we got some kind of tag in here. And so we're doing those branches, but all wrapped within these if statements instead of inside of blueprints, right? And then we're calling our functions a particle and counterparticle. So let's go ahead and take a look at those two functions. So what we've got is our particle setter requires an input, the vector for the anti-vector for the particle systems, those tags, and then it takes an owner and then a float called param. That param is the thrust. So in our blueprints, if we're looking at, our particle setter here, this is our param right here for the set float parameter. And so we're just calling in all of these things and then basically doing the same checks. We're just going if fmath is nearly equal, do these, and then we're doing our for loops for ps Victor, and then we're doing basically these for loops though are for each loops because it's going to say for every particle system with that fname tag, and it's going to go through the vector ps. So it's going to go for each of these. Go ahead and do this thing. So what are we actually doing here? So we're going in. So we're basically iterating over each one of the particle systems that are tagged by the tags given in vector ps. We're saying, okay, once you go to that next one, we're going to call this code. And what this code is this is an array. Basically right here, I create a temporary array to a pointer of a Niagara component. And basically I get that component by calling get components by my tag, and then I'm passing the uNiagara component and then the owner and the particle system. Now this right here is something that is a template that I've created. The way you can kind of think about templates is they're kind of like functions, but not quite. Templates are a way to call a piece of code or a piece of a set of instructions, but while leaving the actual return type or what's known as a template a little bit more generic. It's called a type name. So as an example here, right, we have our template type name T, and this T is just basically a placeholder for here's the type that we're going to give you, and we want a pointer to that type. And then from here, if we actually step into the template, what we're doing, let me make this a little bigger for you. When we're stepping into this template, what it's saying is, okay, so you've given us a type and we're looking for that type. And here's our input params, right? So first it's going to say here, create a temporary result array of that template type. From here, we're then going to actually create a array of components that are a pointer to a uActor component. And we're going to set that equal to getting the original actor says the owner that we passed in. We're going to go to that actor pointer and we're going to get components by tag, and we're going to pass in the static class of that original template type name. So for example here, whatever we passed in as the type, and we're going to pass that as a static class to the get components by tag, and we're going to pass in the tag that we want for that specific one. With that, we're going to then have an array of those components of those Niagara components. And we're going to say for each of those components that are a uActor component pointer, we're going to go ahead and say if the type name or typed component here is equal to a cast of that type component. So basically, like if these match, then we're going to go ahead and add the result. Because in theory, when we're getting these generic actor components here as an array, you could get Niagara components, you could get audio components. There's all kinds of things you can get. Now you do pass in the get components by tag, which should return them as a T subclass of that uActor component. But in theory, if you have like a wrong tag or something, you could get mismatches on the class. At least I've seen that. So to prevent that kind of error, we just here basically force the cast and say if this matches, then go ahead and add the typed component here. So just make sure it matches. If so, add it here. Once it goes through every single component, then it returns the result. And that result from that template is then being passed in back here, as you can see, into our temporary array. From here, we just check the initial 0. Is that equal to a valid level? Because as of right now, just by default, I'm only having the one at a time. Basically, for each vector PS, that's only going to match to one Niagara system. In theory, in the future, I could have that match multiple. But for the most part, I'd rather pass in more tags and have to make a new tag for each and every single one of the engines I want to trigger for this section than the reverse, which is everything with this tag gets fired. But I tried to make it as flexible as possible so that I could fire it either way. This is the only part that would need to be slightly tweaked. So for now, I'm just saying, is this a valid level? Which is basically just a way to check of, is this valid? Does this exist? If it does, then go ahead and set the float parameters to user.rocketOn and the 0, 0. We basically do that exact same set of calls everywhere else, except we're doing the either anti-vector or we're doing it with the param being passed in, depending on if we're thrusting or not, if we're anti-thrusting or not, that kind of thing. I know it's a little complicated, but basically this is just templates are a very easy way to make your code more flexible when you don't necessarily know what specifically, or if you're wanting to have multiple return, what specifically is coming back with those components or with whatever you're using your template for, right? Because this can make it so you could return a lot of different options. Maybe you want to have ints and floats returned, and then you'll go ahead and do some comparisons and figure out, what data you want, what data you don't, depending on what's actually returned. From there, we'll take a look at our counterparticle. Our counterparticle is actually quite simple, kind of like our blueprint one. Basically, it takes in all the same input parameters, except it takes an additional one of current speed. From there, it basically goes, is the current speed absolute greater than 0.001 and the input is equal to 0? If so, we're going to call that same particle setter above, passing in our current speed as our input, and then vector, particle system, anti-vector, particle system, owner, and param. And here I'm doing a little logging of roll speed because I was checking out some values on the way the roll worked. So with that, that is basically the way these different particle functions are called, and then they're just wrapped in with these if it exists kind of functions. But yeah, so I know that's probably a whole lot to talk about. And just to give you guys a little bit more detail, if we go to our, I believe it is our, where is it? Sorry, I was looking in the wrong place. So if we go to our build.cs file, if you are going to do something similar, you want to make sure to include whatever are the appropriate dependencies. So for example, right, you might want to include Niagara or anything like that. For example, see, I don't have that included here. I've got Niagara included, but that's because I've used it elsewhere. But if you're going to want to use any of the Niagara functions or anything from Niagara, you'll want to make sure to include that in your build file. But yeah, all of that condensed down basically turned that massive function into basically just these three right here. So let's actually take a look at some numbers though. Let's see what kind of difference that made for us in terms of the actual performance of our game. So let's open up our trace files here. So if we go ahead and start Unreal Insights. All right, if we go ahead and put them side by side to kind of give you a good idea, on the right hand side is the previous way and the left hand side is the C++ way. If we go ahead and just look at the check particles here, as you can see, it's basically cut it down to a third of the actual processing time. And while that may not necessarily seem like a whole lot, shaving off 0.4 milliseconds doesn't necessarily seem like a whole lot on its own. This is just with, a handful of particles running on a single ship. This is not accounting for if you've got, 10, 20, 100 ships, you might then want to look at this as more multiplicative. If it's 0.6 for a single ship and you've got 100 ships, then you're going to be looking at almost 60 milliseconds, right? Now it's not as strictly, proportional as that, but just to give you an idea of there's a lot of savings made here. And that's what you want to kind of target when you're looking at making these wide sweeping changes is, when you're cutting down from 629 to 237, that's a savings. If that's only a savings on one single ship, then it's not as big of a deal, maybe not as important. But when that's going to be used by every single ship flying, so my player, my AI, everything's going to use the same particle system, that's shaving off time per ship. Now, of course, you'll want to look at what functions you want to change based on what's going to give you the most bang for your buck. But even small changes like that, even just 0.4 milliseconds per ship, even if it's not directly proportional, let's say it's closer to 0.2 or 0.3, that's still a lot of savings to shave off when it comes to performance. Those things add up and they stack up and can mean the difference between hitting your 60 FPS targets or hitting something lower at max settings or whatever your ideal settings are. But yeah, that's it for today. If you have any other questions or anything else, let me know. But otherwise, good luck and good hunting.